So what are the main properties of these chemicals, the alkanes, the saturated hydrocarbons? Here we go. So for instance, some of the long chain saturated hydrocarbons are used in waxing fruits and vegetables to protect them from rotting. And you may wonder, like, if it's safe. It is safe because hydrocarbons are actually quite inert and they're not uptaken or transformed in any way in the human digestive tract. Okay? But of course, the most important usage of alkanes is for heating. Okay? So these four, methane, ethane, propane, and butane, are used as heating fuels. Okay? Does that make sense? So for instance, when you buy the tank for your gas grill, it's going to be propane. There are some mostly camping equipment that allows you to produce really, really high temperature in a very short period of time, a lot of heat. Those are mostly butane burners. Methane and ethane are used less than that because the proportion of those gases in the overall natural gas composition is much lower. Now, when you start looking at the, that's obviously the people who prepared these slides did a lot of typos. So, pentane, hexane, heptane, and octane are liquids, okay? And they comprise, to a large extent, gasoline, okay? So here's my question. When you go to the gas station and you fill up the tank, you use numbers, right? Like what are you putting in the tank? What number? 87? What does that mean? Fantastic answer. Fantastic answer. So here's the story. That's a great answer. I loved that answer. Because here's the story. It's called an octane number. Basically, when you have an octane and you put it in a gas engine, it burns highly efficiently, and it burns but not detonates. Am I making sense? Do you see the difference? So when fuel is getting into the cylinders of the engine, it should burn, not explode. Burn faster but not explode. Okay? Octane can do that. Octane is very expensive by itself. The actual gasoline contains the mixture of various hydrocarbons. And the greater the octane number is, the less detonation and the less damage to the engine the fuel is going to produce. The engines in overwhelming majority of the cars that are sold in the United States are well suited for the engine for the fuel with octane number of 87. So it's like 87% as good as the pure octane itself. Pure octane is like perfect. Does that make sense? If you start looking at the performance cars, let's say Ferrari, okay? The degree to which the fuel is being compressed within the cylinders is much higher than in my Kia, for example. At this level of compression, the fuel is more likely to detonate rather than burn. So you need to use a fuel with a greater octane number. And since getting to a higher octane number is expensive, when you refine oil, this is why, 95 is way more expensive than 87. But again, most cars do not require that level of performance. Does that make sense? So these guys hexane, heptane, octane, yeah, for sure. They will be substantial part of gasoline. Now, when you start talking about 9 to 17, this is the decane, so 10 carbon atoms. Where are you going to find them? So, motor oils, mineral oils, kerosene, diesel, jet fuels. Here's what I want you to think about. When you go from pentane to hexane to heptane and so on, just increasing the number of carbon atoms in a hydrocarbon, the boiling point increases. I'm going to take a break right there and ask you if you like, I want you to process what I just said. They are denser, heavier, and they boil at a greater temperature. Make sense? So if you would look at things like motor oils, mineral oil, kerosene, diesel, and jet fuel, it's not exactly within the same range, but we're pretty much talking about the following sequence. We have gasoline, which is the lightest. Then we have diesel, which is heavier and denser. Then we have kerosene, which is, surprisingly, a jet fuel at the same time. Then we have, and pretty much in the same ballpark, we have motor oils. Okay? Anything after that, waxy solids at the room temperature. Make sense? So when you go at 18 carbons and beyond, we're talking solids. Now, for the most part, in our day-to-day life, we use the mixture of hydrocarbons. Like kerosene is the mixture of hydrocarbons that have relatively high boiling temperature, but that are liquid at the room temperature. Does that make sense to you? One of the reasons why diesel-powered engines are a little bit hard to start in the winter, because diesel fuel has higher boiling and higher melting point. So when it is cold, diesel fuel becomes super, super dense and requires some additives to keep it liquid so the engine can start. You're not going to have this problem with the regular gas. Am I making sense right now? Now, you can see actually the residues of the oil refining right now in the state of Ohio when different municipalities prepare the roads for the winter. I don't know the proper term in English for this, but you know this like black tar that they put on the roads? That's hydrocarbons. That's the mix of really, really dense liquid ones and a bunch of solids. Okay? They're really hydrophobic. They prevent water from, getting in the cracks and whatnot. Okay? So Vaseline is the mixture of different hydrocarbons. This is just an illustration to the points that we've just made. 1,4 carbons. Okay, we're talking about gases, so lighters and stoves. 5,8 gasoline. 9,7 something denser, heavier than gas, like kerosene or diesel fuel or motor oils. And 18 or more solids. Okay? So far, does that make sense? Good? Now, another bit of information, and you can ask how I know that. I worked for a company that was trading motor oils. So when you go and buy motor oils, there are conventional and there are synthetic, right? I mean, there are synthetic blend. Okay, so what is the conventional motor oil? We take regular oil that we pump out of the ground or bottom of the ocean, right? And we separate it basically by distillation. Like when people do moonshine, they, distill. We do the similar stuff, okay? So the super light fraction becomes the gas fuel, like the gasoline. Heavier fractions become conventional motor oils. They're decent, but the components of this oil get oxidized very quickly and the oil loses its lubricating properties. That makes sense? This is why, if you want better protection, I'm not advertising, I'm just telling. If you want better protection, that heavier fraction will go through, oh crap, I forgot the name. This is a disaster. So basically it's the thermal treatment of hydrocarbons which makes them branched. Will probably come up by the end of the class. There's a special name for the process. Anyway, this is why we call it synthetic. It's not like it's completely synthesized from scratch, but they undergo pretty heavy treatments to make them more resistant to oxidation and to last longer. Like conventional oil you change every 3,000 miles, synthetic you can change every 7. Okay, because they're more resistant. This is why they're more expensive. Make sense? Okay. So in terms of the solubility, it's not it shouldn't be a surprise to you that these chemicals that consist exclusively of carbons and hydrogens and have non-polar covalent bonds are non-polar and insoluble in water. Okay? They are also, for the most part, less dense than water. When we're talking about like super heavy hydrocarbons, super dense hydrocarbons, they're going to sink, of course. But gasoline is going to float on the water surface. Oil itself is going to float on the water surface because its density is lower. The surface. They flammable, they found in crude oil, yes. Now, flammability, one of the favorite jokes, not practical joke, if somebody asks another person to like extinguish a cigarette butt in the gasoline, can you do that? You can. Yes. Here's the thing. You need to know how to do that. I'm not saying you should. What's flammable in case of gasoline is vapors. That makes sense. So I can have like a bowl of gasoline. I can have a cigarette butt. If I stick it fast enough in the gas, it doesn't have time to ignite the vapors. And since there's no oxygen in the gasoline, it's going to die out. Gasoline doesn't burn by itself. It needs heat and oxygen. When you stick that cigarette butt fast enough or a match fast enough, it's just going to get extinguished. Did that. Okay, so it's a vapor that will burn, that will explode, do stuff like that. Clear? Okay. So yes, you all know about oil spills. That's a problem. Oil will float on top. And if any animal gets into that oil, it will stick to the feathers or skin if it's, whatever's on the surface. And I mean, it's an advertisement from people who make dish detergents, but not. They just showing off. But in reality, any dish detergent will remove oil because, well, that's what they do. They remove oils. Okay, just kind of a pain in the butt to do that. But of course, the main usage of alkanes is for the fuel, so they can be burned. So when you break down, you oxidize carbons in the reaction of combustion, you get carbon dioxide and water. Okay, so the simplest one here is the methane. Okay, so I need to correct these people because they don't really know what is the main component of the natural gas. So the natural gas that we use to cook our food is mostly propane. It's not that terribly important, but it's mostly propane. Okay, it's not methane. Now, butane So propane generates a certain amount of energy, okay? Butane also generates a certain amount of energy. But the thing is, every molecule of butane contains more carbons than propane, right? Because propane is CH4, and this is C4H10. Can you see the difference? Since it has, the butane I mean, since butane has more carbon-carbon and carbon-hydrogen bonds, when it is oxidized, it releases more energy per mole. Am I making sense? Because we package more bonds into the same molecule. Are you following me so far? Now, if you remember our conversation about gas laws that we had quite a few weeks ago, we mentioned that at the normal conditions, 1 mole of any gas occupies the same volume, 22.4 liters. Remember we mentioned that? Now, 1 mole of methane will be 22.4 liters. 1 mole of butane will be 22.4 liters. But those 22.4 liters of butane will pack way more energy than the same methane volume. This is why butane is used in camping equipment, because basically this little container will pack more bang for a buck. Okay, and it's like, you know, you can carry it with you just as well as methane, but it will generate more energy. Okay, now here's my question. Gas, a natural gas, the pure natural gas, does it smell? It doesn't. But if you have a gas stove or you have that propane tank and you open it and you're not burning it, or we did it in the lab, do you smell the gas? What smells? Why does it smell? It shouldn't. It has no odor for humans. So there's a compound that's added to the gas to give it odor so we can detect the leaks. The compound is called, not for the exam, ethyl mercaptan. And interestingly enough, it is the same compound that gives human feces very distinctive smell. But we add very small amount, so even if the leak is super small, you can still sense it. So now we're going to try and write the balanced equation for the burning of propane. So remember, the combustion is the reaction between the alkane here, C3H8, and oxygen to produce carbon dioxide and water. Make sense so far? All good? So, we can do it the old-fashioned way. Just do carbon, hydrogen, and oxygen. So in terms of the carbons, we have 3 on the left, 1 on the right. We have 8 hydrogens on the left, 2 on the right. We have 2 oxygens on the left, 3 on the right. Everybody agrees with me? Actually, check me because I may miss something. Okay? So what would you do first? What coefficient would you put in where? Which element you want to do? You want to balance first? Carbon. So you're going to put 3 here, right? So now, on the left, nothing has changed. So we have 3 carbons on the right. We have same 2 hydrogens. And we have 7 oxygens. Okay, sounds good? What would be the next step? Hydrogens. I would put 4 here. Okay. So now we have 3, 8, and 10. Check my math. I think I'm right. Yeah? Am I correct? I think so. We have 4 oxygens from 4 water molecules and 6 oxygens from 3 CO2 molecules, right? The rest is easy because you got carbon balanced, hydrogen balanced. All you need to do is balance oxygen by adding 5 on the left. Okay, so that's your combustion of propane. And yeah, we can write it down that it's 3, 8, and 10 on both sides. All good? Questions about that part? Pretty straightforward. I'm just going to skip because that's what we did. So now we have a couple more types. Alkenes, alkynes. Okay? So alkene is the hydrocarbon that has 1, sometimes more, double bonds. Alkyne has 3. Okay? Does that make sense? So they are essentially unsaturated. As we just mentioned, alkenes contain double bonds, while alkynes contain triple bonds. And we call them unsaturated because you can add more hydrogen atoms to it. There are some bonds that can be saturated with hydrogen, and you can actually make those gases to react with hydrogen, thereby increasing the number of the bonds between the carbon and the hydrogen atoms, and eventually you can turn alkenes and alkynes into alkanes, the saturated hydrocarbons. So this is the simplest alkene, called ethene. So you can see that 2 carbon atoms are connected by a double bond. Okay? And if you start thinking about how this molecule can be organized, it has to be in one plane. So remember when we were talking about alkanes, and we talked about the molecule of methane, we mentioned that it is organized as this tetrahedral structure. Remember, with carbon sticking 4 bonds in all directions, with the angle between the bonds being 109 degrees. In case of a double bond, these molecules are in the same plane. They are flat. And the angle between the bonds is 120 degrees. Okay? So, in other words, instead of tetrahedral arrangement, carbons in alkenes have trigonal planar arrangement. They flat. Like, if you look at me, it's like this. Hydrogen, hydrogen, double bonds. Sounds good? Okay. So ethene is the the proper name. Like this is IUPAC name, ethene. And I'm going to give you some illustration on the naming while we are at it. So remember how we call this molecule it was ethane, okay? So this molecule is ethene. Am I making sense right now? Now, we had this one with 3 carbons before. That was propane. If we connect 2 carbons, the double bond, we're going to have propene. So basically you change the ending ane to the ending ene. Questions? So ethene, so known as ethylene, is actually, it is true, a hormone produced by plants. When bananas are collected, they are collected green. Because, I mean, they're not collected in like Middlefield, Ohio, so they have to travel quite a lot. And you don't want them to go bad, because this is why you don't collect them when they're ripe, you know? And if they arrive to the final destination, or close to the final destination, still pretty green, there are storages that would treat them with ethylene to accelerate the ripening. That makes sense? Like you can do the synthetic one just to speed up the ripening of bananas. Sounds good? Now, alkynes contain triple bonds. Okay? And ethyne, also known as acetylene, another name is you have 1 triple bond between 2 carbons, and you have 2 hydrogens. Does that make sense to everybody? Okay. So in this case, the carbons have a linear arrangement, not trigonal, planar, not tetrahedral, just a linear arrangement. Okay? And this brings us, so some of you, I guess, going to take biology classes, such as, I don't know, anatomy and physiology, maybe microbiology, that kind of general bio, I don't know. But cis and trans isomers is the very important concept in those classes. So we're gonna chat about what they mean. So remember when we talked about isomers, we discussed that it's molecules that have same number of individual types of atoms, but have different arrangement of covalent bonds. Am I making sense? Remember that the structural isomers? Yes, no, maybe, kind of. Okay, I'm going to remind you about isomers, okay? Couple of examples of structural isomers. So example 1, So annoying. Pentane. Okay, so 5 carbon atoms, 10 hydrogen atoms. You can arrange them basically 3 different ways. Well, yeah. You can do this. Do you agree with me? Or you can do this. Trust me, same number of atoms, different arrangement, right? Or you can do this.
I keep counting 12.
My bad. Good eye. Yes. The formula is C15H12. Yes. 12 hydrogens, 5 carbons in each molecule. Right? Structural isomers. Sounds good? There's another option. Now that you know about alkenes, I'm going to present you with pentene. I'm going to be super simple about that. So pentene means 5 carbons, right? But there's 1 double bond. So in an alkane, you have 12 hydrogens. Can you see that? Now imagine you remove 2 hydrogens and use the free electrons that kind of, now free because there are no bonds with hydrogens. You use them to form a bond between carbons. So you make in a double bond. So the formula will be C5H10 or... So let's draw the molecule of pentene. So you have okay, everybody agrees? Checks out. 5 carbons, 10 hydrogens. All good. Can make another isomer out of it. Same number of carbons, same number of hydrogens, different bond locations. Follow? Clear? Good? Everyone? All right? Go ahead. Say it again. This one? It's a double bond. So let me expand it for you. So this is what I mean. I'm not going to draw the entire molecule if you don't mind. So we have a carbon, double bond to another carbon, hydrogen, does that make sense? So this is the double bond between carbons. Better? Okay? All good? Question?
So when you count the bonds between the hydrogen and the carbons, it's 1, 2, 3, 4, 1, 2, 3, 4.
It's always 4 bonds, yes. So if you look at so let's say this is the carbon number 1. It forms 4 bonds. 2 with hydrogens, 2 with the same carbon. This is the carbon number 2. 1 bond with hydrogen, 2 bonds with a carbon on the left, here, 1 bond with a carbon on the right. Did I answer your question? So I can keep working on the isomers of pentene. I can start adding substituents. I'm going to give you just one example. So for instance, I can do this. Okay, different arrangement of bonds, same number of carbons and same number of hydrogens. Does that make sense? But I want to specifically highlight that the universal formula for alkenes is this: CnH2n. Right? Don't know if you remember, but there's another category of molecules that have the same general formula. Cycloalkanes. Any double bonds in this molecule? No. How many carbons? How many hydrogens? This is why molecular formulas in organic chemistry are not useful. You may have two completely different classes of compounds that have the same molecular formula, like this cyclopentane, which is fully saturated, versus pentene, which is not. And yet, based on the molecular formula, you cannot tell the difference between the two. Does that make sense? So what we just discussed, all of this, is structural isomers. Now, any questions on the structural isomers? Like seriously, folks, like I really want you to actively tell me I don't get it. Any questions on this? Does that make sense? So in this case, we change the arrangement of bonds, right? And that's it. Now there are so-called geometric isomers. Cis or trans. So I'm going to pause a little bit on that statement. The double bond is rigid and doesn't rotate. Why? Why doesn't the double bond rotate? Into what? No. So here's my question. Let me expand. So if you have a bond like this, one bond, these carbons can kind of rotate against each other. If you have a double bond, they do not rotate. It's a bit of a tongue-in-cheek question. Imagine two wheels that are connected by an axle. Can they roll? Like each wheel can rotate around the axle. Now imagine some hypothetical idiotic engineer connected these two wheels by two axles. That's it. they're not going to rotate. Am I making sense? Same story. It's like two axles between two wheels. Double and triple bonds do not allow the carbons to rotate. So it's pretty rigid. Okay? So now listen closely. When it says the attached groups, it refers to the groups that are attached to the carbons forming the double bond. Everybody's getting it? Okay? And if you think about this, you can have, if the molecule is asymmetrical, if the substituents or atoms to which these carbons are attached are different, you can have these two arrangements. On the left one, which is called cis 1,2-dichloroethene, chlorine atoms are on the same side of the double bond. They are on top. Can you see that? In the trans 1,2-dichloroethene, chlorines are on the opposite sides. Am I making sense? Can you see that? Like, you cannot, since double bond does not allow for rotation, you cannot change the molecule on the right into the molecule on the left without breaking the bonds. Do you understand what I'm trying to say? Yes or no?
What do you mean by rotate?
So, okay. Let me try and give you an example. It's not going to be perfect because I have to draw a 3D molecule in the plane, but I hope it's going to make sense. So we have two carbons. I'm going to draw dichloroethane, okay? Do you remember the wedge dash model? So if there is a wedge, it looks at you. If it's a dash, it looks behind you. Okay? So what I can do, I can turn the carbon on the right in any direction and eventually make this chlorine looking down. Okay? By rotating simply. When I rotate the molecule around that bond, am I breaking any bonds? I'm not breaking anything. I'm just rotating like you rotate a wheel around an axle. Does that make sense, Evan? Okay. Now, if I want to get from the molecule on the right to the molecule on the left, we essentially have wheels that are connected by two axles. They can't rotate unless I remove one of the axles, rotate, and insert it back. Does that make sense? So in order to get from trans to cis, I have to break double bond, rotate it, form double bond again. It's a legitimate chemical reaction, which means you cannot go from a trans isomer to cis isomer without breaking and forming bonds, which means you need actual chemical reaction to go from one to another. This is what makes them different. Those are two different molecules with different chemical properties. Does that make sense? Okay. This is the nice illustration. Like if you orient your hands in different ways, so like this is cis orientation when the same substituent, a thumb, okay? The substituents are on the same side. And this is trans isomer where thumbs are on the opposite side. Question so far? So now the next four carbon alkene, the butene. So look at this. These are two carbons that form a double bond. Each of them, and I'm going to just write the collapsed structural formula for butene. Does that make sense? This is just a collapsed structural formula. So this is your CH3, that's H, that's H, it's carbon, that's carbon. So since you cannot rotate them, if CH3 groups are on the same side, we call it a cis to butene. If they are on the opposite sides, we'll call it a trans to butene. Does that make sense? 6 out of 10 question. Can you think of a structural isomer of the same molecule, essentially different butene, that would not have cis and trans isomers? While you're thinking, I'm going to write something down just to illustrate. That's cis isomer. Okay. Basically, you need to move one stick. Okay. Two sticks. I'm not going to torture you. Where should I put double bond? To make the isomer that doesn't have cis or trans variants. Where should I put the double bond?
Which one's the isomer that doesn't?
So these two are cis and trans isomers of the same molecule called 2-butene. 2, the number 2, means that the double bond is at the second carbon. Does that make sense? Clear? Evan? Good? Yeah? Okay. Now, I want you to take a look at something. So let's say I'm going to put the double bond at the end of that molecule. Okay? Looks good? Let's expand it. So there's one version. Okay? Everything's right? It's not a tricky question. Like, it looks legit. Everything's good. So what I'm going to do, I'm going to do this. And I'm going to ask you the question. It's the Formula 1. This is Formula 2. Can you go from Formula 1 to Formula 2 without breaking any bonds? You can. You can. Imagine that this is the axis, and you rotate the entire molecule, not just these two carbons. You just flip it. It's going to be the same. Make sense? So you have to have same or similar substituents on both sides of double bond. Because here you have two hydrogens, well, whatever, right? And you have a hydrogen and substituent. It's not going to have cis or trans isomers. Does that make sense? So not every molecule that contains a double bond is going to have cis and trans isomers. But many of them will. Okay? Moving on.
So is it like the isomers have double bonds too, or can be without even double bonds?
Say it one more time.
The isomers, do they have double bonds, or
I think
without the...
so. How about this? I'm gonna answer your question, and then you're gonna tell me if I did answer your question, or your question was entirely about something different. Okay? Are you asking about this? That you can have two molecules with the same molecular formula, like C5H10. One can have double bonds. The pentene.
No, I was asking if isomers only happen to alkenes, those compounds with double bonds. What about if you can take like butane? Can it have isomers?
Yeah. There you go.
It's just one bond.
Look. I'm gonna specifically try, like, look at these molecules right here. They are all structural isomers. Does that make sense? They have different arrangements of bonds, no doubles. We call those structural isomers. Pentene and cyclopentane are structural isomers. Do you follow? But cis-trans or geometric isomers can only exist if there is a double bond present. Make sense? Did I answer your question now?
Yes, you did.
Okay. Yes, they do have different physical and chemical properties. This is okay. So pheromones. Well, I don't think it's the best example. So yes, insects release pheromones, sex hormones, pretty much, that for the most part used to attract the opposite sex. Okay, and so the effectiveness of the pheromones depends on the cis or trans configuration. Okay, that's like, obviously, I will make sure that if something like this ends up on the exam, I'm not going to count it because it's stupid. Yeah, sure. Okay, we have a pheromone, but there's one more important feature of cis and trans orientation. And I'm going to introduce you to this, since we do have some time. Have you heard about trans fats? Yes? Okay. So what is a trans fat? Fats, we call them fatty acids. They have the following arrangement. Remember, this is the line formula, right? Okay? So this is a saturated fat. Good? This will be unsaturated fat. So have a double bond inside. It can be one, it can be multiple, doesn't matter. Am I making sense so far? Now what we're going to do, I'm going to get this part of the fat and expand it, okay? So I have a double bond. Does that make sense? So these two carbons form double bond. Each of these carbons is connected to another one. Can you see that? And to a hydrogen. And these carbons are connected to something else. Whatever. This, whatever. Doesn't matter. So what you're looking at right here, is that cis or trans? Cis. Make sense? This is what you're going to find in oils, like canola oil or vegetable oil or whatever plant oil you're using for cooking. Does that make sense? Now, saturated fats, you get them from animals. I'm talking about like lard or butter, okay? So, let's focus on butter. Butter is tasty. Everybody, well, maybe not everybody, but people love butter. What is more expensive? Animal fat or plant fat? What is more expensive to make? Well, even like if you go to a grocery store, what's more expensive? But, dude, the package of butter will cost the same amount of money as a huge bottle of oil. By mass, plant oils are much cheaper to make. Like, you grow them on it, you don't have to take care of them, they're not going to die of like some horrible infectious disease, you know. You see what I'm saying? Like, plant oils are very cheap to produce, like corn oil, canola oil, very cheap. The only problem is that they're liquid and you can't put them on the bread, right? I mean, yes, you can, but it's not a butter. I mean, you definitely will believe it's not a butter. But what if you bubble some hydrogen through this double bond containing cis double bonded unsaturated fats to make them saturated? You can do that. And you're going to make saturated fats, basically going to make margarine or vegetable shortening. Okay? Solid? Absolutely. Spreadable? No doubt. There's one little problem. When you do that, one of the side products is this. You have double bond. Now, what is this? Cis or trans? Turns out, trans fats, they really mess up your blood vessels. Like, seriously mess up your blood vessels. By the way, just FYI, butter, bacon, pork, not going to contribute to cardiovascular disease risk. Obviously, if you eat like 5 sticks of butter a day, they will, but at like normal person's consumption, if you drink like, you know, few cups of milk a day, and eat bread with butter and eat a pork chop from time to time, you're going to be fine. That does not contribute to cardiovascular disease. Trans fats, on the other hand, do, and they are really, really bad for your health. Make sense? So this is why it's important to understand the differences between the cis and the trans. Double bonds. Okay? Question so far?
Is there a way you can test in the RABU to see how if the compound has those double bonds and observe them?
Can you check if the compound has double bonds? Yes, you can.
Or 3 bonds, yeah.
You can. And you can figure out if they are cis or trans. Yes, you can. Make sense? Is that what you're asking?
Yeah.
Okay. Yeah, you can absolutely, you can detect it. There are reactions that are characteristic for compounds with double bonds, but not without. Okay? Naming, which is, you probably have figured it out already. It's a cis versus trans. And when you have a molecule like ethene, you don't need to let everybody know at which carbon the double bond is, because there are only 2 carbons, okay? So we're going to name this. So 2 carbons, what is the prefix? ETH, right? I'm going to put it a little bit to the right. Double bond means ethene, right? Good? Sorry, my bad. I'm an idiot in this case. It's not ethene, and you didn't correct me. How many carbons in total we have here? 4. What is the prefix for 4? Anyone remembers? Butene. Okay, sounds good? Good? Now, we need to let people know what position the double bond is at. So we're going to number carbons. 1, 2, 3, and 4. So double bond is between 2 and 3, right? It doesn't matter from which end you start numbering. Do you see that? So it is going to be 2 butene. 2 means the double bond is at the position 2. Am I clear? Then you have 2 substituents. Both of them are chlorine atoms. So since you have 2 chlorine atoms, dichloro, am I making sense so far? These chlorine atoms, where are they? At which positions? At which carbons? 2, 3 dichloro, 2 butene, and the substituents, are they on the same side or opposite sides? Cis, 2, 3 dichloro, 2 butene. Does that make sense? Now, I want you to take a little bit more active participation in the next one. I don't want to answer any of my questions. You're going to be answering them. How many carbons? 4. 4. Do you see all 4 carbons? Right? So what would be the name? Butene, because there's a double bond. Double bond is at which position? At which carbon? 2. What are 2 substituents? Bromine. So, how many bromine atoms do we have again? What should I put in front of bromo? At which carbons are both bromine atoms? Are they on the same side or opposite sides? What should I put in front? I sense the desperation and puzzlement in the air. Think about the steps. Number of carbons. In the longest chain. Okay? So you need number of carbons in the longest chain. Then you ask yourself a question, double or triple bonds? I can promise we're not going to be talking about multiple double or multiple triple bonds. Okay? We're at which carbon? Remember that you want the name with the smallest numbers. So in the examples that we have on the slide, the double bond is between 2 and 3. We choose 2 because it is less than 3. Am I making sense? Okay. Do you have substituents? Maybe. Hydrogen is not a substituent. Quick question about the first or second example. Technically, there's a methyl groups. Why we don't consider them as substituents? Look at the very first number in that list. They are the part of the longest chain. Does that make sense? Okay? We're at cis or trans. Does that make sense right now? For C, I would appreciate if you can just produce the name. Hydrogens are not substituents. Trans, Jackson, 2-butene. Does that make sense? Because there are no substituents. This is your longest chain. Making sense? Go on. This number? you need to kind of let everybody know what position the double bond occupies, right? So you start numbering 1, 2, 3, 4. What position? Position 2. Why not 3? Because 2 is less than 3. Now, we're obviously not going to look at the solution. We got it all right. I'm gonna give you some exercise. Just what I'm going to do now, I'm going to give you an example that is perhaps more complicated than anything you're going to see on the exam. But it's easier to, do it here in the class and then be comfortable on the exam. So let me just draw a molecule. I'm completely just making it up in a good way. Right, so let's do this. So we have carbon, we're going to put double bond. We're going to put chlorine, this, and this. I have no idea what I'm doing. Like, seriously, I'm just improvising, okay? So this is the molecule that we're going to name. Sounds good? Now, what do we need to do first? Number of carbons in the longest chain. We can, so one little mistake I have here, let me correct myself. It's CH3. Okay, that's all. So what is the longest chain? Either this or, this, right? It's the longest chain. How many carbons in total? 7. Double bonds? So the ending is E-N-E. Okay, at what carbon? Any other options? So you number from left to right? But what if you number from right to left? Third carbon. You want it to be the minimal one, right? So 3-heptene. Does that make sense? Good? Now let's do substituents. What is the order? This is really hard. This is legitimately like an org chem question. What substituents do you see? Let's start with this. Chlorine. What letter does it start with? C. Any other substituents? Bromine, which letter? So it should go first. Any other substituents? Methyl, so let's put them let's color code them. Okay, makes sense? Everybody? What should go first? Bromo. Well, how about we're going to start from the last because it's easier for me to write from the right hand side. So the last one is going to be methyl, right? We need to figure out the position. So we need to number 1, 2, 3, 4, 5, 6, 7. So 6-methyl. Next. How many chloros? 2. Di. The positions. Orientation, cis or trans. And we have one more left. Two bromo, trans 3,4-dichloro, 6-methyl-3-heptene. The organic nomenclature is absolutely crazy. When you start looking at the names of really, really big molecules, they now have developed, I'm not familiar with this, they have a special code which makes the really long names much shorter. So they don't use chloro, bromo, there are special codes for it. We're not studying this, and honestly, when I was studying OrChem, we didn't have it like that. Okay, but this is insanely huge. Nothing like this is going to be on the exam, trust me. It's going to be simpler, so the complexity will be in that ballpark. Okay? Make sense? Go on.
What's the reason we don't start with trans, bro?
Just to show that trans belongs to dichloro. That's it. We didn't have any options before that. This is what I was talking about. Oil hydrogenation. So, when you hydrogenate vegetable oils, you produce solid, cheap spreads, but they also contain trans double bonds, and they're not good for your health. So the last bit for today is to discuss so-called aromatic compounds. So they have, okay, I'm going to skip the introduction. We're going to jump straight to the benzene. So this is a foundational, the simplest aromatic compound. If you wonder if aromatic compounds smell, or do they? They don't smell, the smell is not pleasant, it's not revolting, but it's definitely not like enjoyable. Okay? So the basic aromatic compound is the benzene. I'm going to skip ball and stick model and I'm going to jump straight to this. So you can see that there are, and I'm going to blow it up, that there are 3 double bonds within that ring. Okay? And you can see that they are separated by a single bond. Am I making sense? So you can represent benzene by these two formulas that differ from one another by the position of double bonds. Am I making sense? Do you understand what I'm trying to say? Okay? So these structures are called resonance structures, which means that at every given moment, every molecule in benzene exists either as the left or the right structure, and they have no difference in terms of the chemical properties. Am I making sense? Okay? And here's the kicker. So we talked before that every chemical bond is basically an electron pair. Does that make sense? Good? So if you would look at the actual distribution of electrons in the molecule of benzene, before we get there, I want to ask you this. So we have, let's focus on double bonds, okay? So this, and this 3 double bonds. The extra bond, the one that makes it double, is basically an electron pair. Okay? So this extra, the second bond, is 2 electrons. This bond the extra bond is also 2 electrons, and this extra bond is also 2 electrons. Do you agree with me? The extra bonds. So we have a total of 6 extra electrons. And we have 6 carbons. In the benzene molecule, those 6 electrons do not belong to any individual carbons, but instead are distributed equally around all 6 of them. This is why the typical formula for benzene isn't with double bonds, but with a circle inside that represents that equal sharing of electrons among all carbon atoms in that cycle. Understood? This is why we have the circle. There are a lot of chemistry of aromatic compounds is much more interesting than the chemistry of linear, or what we call aliphatic hydrocarbons. This is trinitrotoluene, or TNT. So I didn't tell you this, but if you can get your hands on some cotton and some 100% nitric acid, you can make what's called trinitrocellulose, which is used in gunpowder. I know that because we did that first year in college in inorganic chemistry lab. We just got a bunch of cotton, stuffed it in a beaker, covered with nitric acid, 100%, sealed it, put it in a cabinet, waited for a week, took it out, drained the acid, rinsed the cotton, dried it, set it on fire. It was marvelous. Like a gunpowder. We basically made a gunpowder. Trinitrocellulose. And if you replace this methyl group here, if you replace methyl group with amino group, you're going to get picric acid, which is an explosive that was used before the discovery of TNT. TNT is much more stable compared to picric acid. It's still not great, but it's much more stable. Picric acid would explode if it's dry, just will explode by itself. And a friend of mine set up a lab to prepare it. She did it, and the picric acid just spilled on a hot plate. And she didn't want it to blow up, so she just wiped it with her hand off the hot plate. And luckily everybody was alive, but her hand was bright yellow for like 2 weeks or something. Acetaminophen, you see, the benzene ring, that's Tylenol, okay? Aspirin, everybody knows what that. Vanillin, that's vanilla taste and vanilla flavor, okay? Concept map. I promise we're going a little bit ahead, which I'm happy about. We're going to take about 7-minute break. And when we'll come back, we're going to start talking about alcohols, diols, and ethers. And I want to carve out some time before the third exam to give you a better understanding what types of questions you can expect of.